So today we're going to look at problem solving for chapters 9 and 10 in preparation for the last exam. And my objective is to finish this with plenty of time so that we can do the lab, because this is a fun lab and I don't want to rob you of that pleasure. Okay. So I got some, I took that composite document and highlighted some like I normally do now. And so you can see which ones I'm going to focus on. Get off. Okay, number one. I'll just write that up there for benefit of our viewing audience. Which of the following general reaction types is characterized by there being a single reactant? So you've got something here, that's all there is, and it makes something else, right? So probably not a combination. You need two things or more. Decomposition looks like a candidate because this would make something else like a B and a C. Displacement, no, you need two items there also. Exchange, and you need two items there. Okay, so decomposition seems like a logical one. All right, how about number 4? The proper assignment of oxidation numbers to the elements in the polyatomic ion SO3 2- would be what? So there'll be an assignment for S and an assignment for O. O is based on the rules. It's always a -2. Right? Unless it's in a peroxide. Remember that. What is it if it's in a peroxide? Think of it this way. There's a peroxide with something else. So think always -2, except in this case, -2 is for both of them. That makes each one -1. Okay, maybe that'll make it a little easier to remember. Okay, so let's get back to this one. The total of our oxidation numbers has to equal the charge on the polyatomic. So we've got a -2 times 3 is a -6 for the oxygens. But we got to hold a couple of negatives out for the charge. That means we really only have to balance a -4 with sulfur. So sulfur then is a +4. Okay. And that would be D. Okay, +4. Wait a minute, that's not right. +4 -2. I was pointing the wrong one. Let's see, 6 is a little shaded there. Let's move it up. Okay, that's good. So which element is oxidized in the following redox reaction? It tells you it's a redox reaction, so you don't have to deal with that question. See, am I still on the board? Barely. But you can deduce that it's a redox reaction by our rule of thumb, right? You got an element here, it ends up in a compound over here. That's always redox. So this is an element, which means it has to be a 0. This is an element, it has to be a 0. Okay. Now, water should be actually memorized. That's 2 + 1 for those. This is the one that might give you some pause. We have to go back to the rules. So hydrogen is going to be a +1. That means +2 total. This one has to be a -2 to balance. Okay. Now we can say which element is oxidized. So oxidation is loss, right? Oil rig. Oxidation is loss. Who lost electrons? Well, oxygen gained electrons. Hydrogen didn't change. Sulfur lost. sulfur lost 2 electrons. So sulfur, this compound, sometimes the answers show up as, oh, that's good, sulfur in H2S, that's right. So this is the reducing agent. It was oxidized. So if this is oxidized, what if that were in a galvanic cell? What would we call it? Where would it be located? Oxidized. Yeah. Well, I'm thinking of terminology. I'll give you a choice. Cathode or anode? Okay. Right. Yeah, 50-50 chance. Cathode's reduction and anode is oxidation. Okay. 6 and 7. I'm going to have to get that one over here. Scroll it to. There's 2 of them. And we get those 2. 7. I need to write my numbers larger. They show up better in the video. Which substance functions as a reducing agent in the following redox reaction? So we've got this reaction, which is already balanced for you. Just barely. Okay, so the reducing agent is the party that's oxidized. We have to find out which one was oxidized. Right? That one's a 0. Right? This one's -2 plus 1. So oxygen is reduced. This one's a -2. This one is +4. Okay. So if oxygen is reduced, then it's not the reducing agent. So we look to carbon. Carbons are most likely a candidate for this one. Over here, we've got a +1, +4 total. That means this carbon is a -4. So yeah, that carbon lost how many electrons to go from here to here? I always find it easier to go, all right, how far is it to 0? -4 to 0 means it would lose 4. But then from 0 to +4, it loses 4 more. So it's 8. Lost 8 electrons to go that route. So if carbon in methane lost 8 electrons, it is the reducing agent. It causes the reduction of oxygen. That's why methane is the answer. Okay. Number 8. Okay, look kind of funny for a second. I saw some big O's and some little O's. It's supposed to be that way. Yeah. Cobalt versus carbon. What's the change in oxidation number for the cobalt in the redox reaction? So we got 2 CH203. Yep. And then 3 carbons. And then 4 cobalts. And then 3 CO2. Okay, change in oxidation number. So we just look at the cobalt, right? -2 for oxygen, -6 here. That means +6 balanced with this cobalt, which means each one has to be +3. Okay. On this side, cobalt is an element, so it's 0. So the change in oxidation number goes from +3 to 0, right there. Okay. Let's see who's next. And of course, it'll make me test my manual dexterity. Another one. That's good. Number 12. The minimum combined kinetic energy reactant particles must possess in order for their collision to result in a reaction. The minimum kinetic energy required for a reaction to proceed. There's a name for that. Right? Remember? You have some choices. Right, we're looking at this diagram, remember? Where you maybe start like that and go down like that. Energy's over here. Right, we're talking about, this is the energy level for the reactants, this is the energy level for the products, and this, between here and here, is what they're talking about. The amount of energy required to get that reaction to go. And we abbreviated activation energy. Okay. Maybe your brain's a little foggy now. I understand. 13. Whether a reaction is exothermic or endothermic is determined by what? Well, I should have left the diagram up there. If the reactants have more energy than the products, it's exothermic. Because that energy's got to go somewhere. You can't create or destroy energy. So if you had more energy to start with and less energy afterwards, the energy got to go somewhere, and that's out. That's exothermic. It's the other way around, and you have more energy in the products, then it's endothermic. So let's see which one fits that. Whether a reaction is determined by how reactant and product potential energies compare. Look at the total energy of your reactants, total energy of your products, compare the two. Right. It's like I got 14 and 15 on there. Which of the following changes is most likely to decrease reaction rate for a chemical reaction? We're going to decrease, for this chemical reaction. Okay, so we say 2CO plus O2 yields 2CO2. So we're looking at the reaction rate. And we want to decrease it. Reaction rate, okay. Adding twice as much oxygen to the reaction mixture. That should increase it because you've got more reactants there initially. That means there's more chance. This is statistical. There's more chance of encounter between this reactant and that reactant. So it should proceed faster, at least in the beginning. So A is not it. Tripling the temperature of the reaction mixture. Usually, increasing the temperature will increase the reaction rate. Adding a catalyst to the reaction mixture. That'll increase the rate also. That's the whole purpose of a catalyst, to increase the rate. Removing some CO from the reaction mixture. If you take away some of the CO, it's going to actually favor the reverse reaction, which will slow down the forward reaction. Does that make sense? Okay. It's kind of it's more intuitive than it is quantitative, because we know that equilibrium is a separate topic from kinetics. Those are two different topics, but they do have some overlap. And I think that's what we're getting at here. Is that we know that the equilibrium will shift. If we remove some of this and it's already at equilibrium, then it'll go backwards. So by one way of thinking, removing some of this, if it's not at equilibrium and it's trying to go this way, removing some of that will decrease that forward reaction rate. That's the best explanation I can give you. Trying to read the author's mind. Or is it mine? More than one author of this textbook, I think so. Okay, 15. Catalysts are correctly characterized by each of the following statements except one. So which one is wrong? They can be either solid, liquid, or gases. Right? That's true. They lower the activation energy for a reaction. Yep, that's what speeds them up. They lower the activation energy. They actually provide an alternate route for the mechanism of the reaction. You end up with the same products. You just get there by a different, faster route with a catalyst. How about C? They do not actively participate in the reaction. Oh, false. They are intimately involved in the reaction. It's just that macroscopically speaking, the catalyst goes in this side and comes out the other side, ostensibly unchanged. But the mechanism is an intimate involvement of the catalyst. So we actually found our answer. D should be true also. They're not consumed in a reaction. That's true. So C is the answer to 15. They are definitely involved in the reaction. 17, that looks like we got all of them there. Let's see, it's going to take some. Which of the following is the correct equilibrium constant expression for this reaction? Okay, so we've got a balanced equation. Just write it correctly. Oxygen. And the phase is important when you're writing a equilibrium expression. Why? Because pure liquids and solids drop out. They don't participate in the equilibrium expression. So it has to be either aqueous or some solution type concentration or gas. Solids and liquids disappear. H2O, this is gas, and 2Cl gas. Okay, so normally what you would write here is what? Product of the products concentrations. So we use a square bracket for that, remember? Water's a gas, so we keep it. Chlorine is a gas, so we keep that one. But we need the coefficients as powers. Okay. Now we need the reactants go in the denominator. So we need a concentration of hydrogen chloride gas to the 4th power, and then oxygen gas to the 1st power. So we should be able to find this one over there somewhere. Let's see. No, there's no powers there, no powers there. There's powers. Okay. There's powers, but the wrong powers and the wrong elements. Cl, water, HCl4. That's it right there. C. And we didn't have to lose anything in the expression because they're all gases. So what does that tell you about the reaction environment? Look at that one right there. It's got to be greater than 100 degrees, right? Probably more than that, a lot more than that, in order to be a gas. Okay, let's see. 18. Le Chatelier. What is the Chatelier state? it states that for a system at equilibrium, if it is disturbed, the system will react in such a way as to mitigate the disturbance. Now, we got anything in here that matches that? Let's see, only exothermics? No. Only reactions with a catalyst? No. Chemical equilibrium is disturbed, the system will try and reestablish equilibrium. That's it right there. We don't even have to look at the last one. So, got 18. Moving on, 19 and 20. CO2 and H2 are allowed to react until an equilibrium is established as follows. Okay. What will be the effect on the equilibrium of removing CO from the equilibrium mixture? I'm not going to write the equation because it's already there. If you remove carbon monoxide and it's at equilibrium, what's it going to do? It's going to sit there and twiddle its thumbs. No. If you remove CO, it's going to shift to replace some of that CO. It's going to shift to the right, as written. Okay? That's how it responds to a disturbance. So let's see. What is it saying? Equilibrium will favor the side of the reactants? Nope. It'll favor the products. H2 concentration will double? No, it'll decrease. Definitely won't double. CO and CO2 concentrations will, no, I don't think so. You're going to decrease CO2. H2 concentration will decrease, yes, and water concentration will increase. There you go. That's what will happen. Now, that's an equilibrium shift. What effect will that have on the equilibrium constant? Zero. No effect whatsoever, because it's a constant. We didn't change the temperature, so the constant won't change. How about the equilibrium position? What effect will that have on the position? Yeah, it'll change the position. You'll have a different set of concentrations for each one of those. But in the once it's reestablished equilibrium, then you take those new concentrations, which will be different than the original ones, put them in your expression, and you'll find that they will give you the same constant value, equilibrium constant. So when you remove some of this, some of it will be replaced, but not all of it. But you will make more of this than you had before, and you'll lose some of that and lose some of that. So that's what I mean by equilibrium position. The position changes, the actual concentrations change, but the constant doesn't, because we didn't touch the temperature. About 20. According to Le Chatelier, which of the following changes will shift the position of equilibrium to the left for the reaction? Notice in this case, we've included the energy term, heat. This is an exothermic reaction. So which of these will shift the position to the left? Double the concentration of N2. Now that'd go to the right. Decrease the concentration of ammonia. No, that'll go to the right also. Increase the concentration of H2. That'll go to the right. Triple the temperature. If we treat the temperature as a reactant or product, depending on whether it's a reactant would be endothermic, product would be exothermic. When you change the temperature, you can look at it that way. So we've added heat, it drives the reaction backwards. So D is the answer. That was the problem that Hopper had when he first was trying to make this reaction work. He knew it worked in the laboratory, but he wanted to create it on an industrial scale. He knew the reaction was exothermic, but he knew the reaction was very slow. Its kinetics were very slow. So he knew he could speed up the rate of the reaction by increasing the temperature. The problem was increasing the temperature drives the reaction equilibrium back to the wrong side. So the way he overcame that was he introduced a catalyst. So the catalyst made the reaction proceed faster to the right, even though the equilibrium was to the left. It happened so fast that all he had to do was take the reaction mixture and run it through a continuous cooling cycle, bring some of it outside, cool it. The ammonia has a much higher boiling point than nitrogen and hydrogen. So the ammonia would condense out of the mixture, drain the ammonia off, and send the reactants back into the reactor and just keep cycling like that. So eventually he got it to better than 15%, which was pretty good in those days. So he had problems to deal with, and that's how he solved them. Okay, that was 20. Have I told you that story before? Okay. I always try to get that one in every chemistry class, because it's got so many things there together. It's got equilibrium, it's got kinetics, it's got history. Right? Haber was making ammonia, so his country, Germans, could make explosives. You can convert ammonia into nitrates, and there you go. You got explosives. Okay, 22. In which of the following compounds does chlorine have an oxidation number of +5? Okay, so we need HClO, KClO2, calcium, chlorate, and more than one or none. Okay, so we just need to do these and see if we can find +5 oxidation state. All right, oxygen's -2, that's +1. So we have a balance there so far of a -1, right? These two together make a -1. That means this one has to be a +1. So that's not the answer. This one's -2 times 2 is a -4. And all alkali metals are +1. So a -4 and a +1 is a -3. Right? So -3 has to be balanced with a +3. So that's not it. How about this one? This one is -2 for oxygen. And that means -6 here. But we got 2 of them. So that's a -12, right? Okay, give it a second to sink in. All right, then we have to balance against this +2. So +2, and that one means -10. So that means this chlorine has to balance with a +10, but there are 2 of them. So each one is a +5. There it is. C is the answer. Okay. That parentheses tends to stump some people and throw them around.
C is correct for 22?
Ooh, that's wrong. Right? Because this one would have been +3. Right? So that's wrong. Let me make that correction. 22 should be C. All right. 23. In which of the following sequences of sulfur-containing ions are the ions arranged in order of decreasing oxidation number? Decreasing means they become more negative. They might be all positives, but they become more negative from left to right. So let's see, what do we have here? We've got sulfite, we've got sulfate, we've got sulfide, and we've got thiosulfite. Thiosulfate. S2O3. 2 minus. I think that's all of our choices. So we need to do the oxidation number for each of the sulfurs. Right? This would be total of -6, right? But we hold 2 of them out, so we only need a +4 to balance it. How about this one? That would be -8, hold 2 out, -6. This would be a +6. There's a -2. This would be, let's see, -6, hold 2 out, -4, +4, but there are 2 of them, so each one is +2. Okay, so decreasing oxidation number. The oxidation number gets smaller, gets more negative. So we've got anything starting with sulfate. Got a sulfate there. Let's see if this one works. So +6, then +2, then -2. That one works. Okay. Can't be this one because that one goes backwards. That one increases oxidation number. This one starts off at +2 and goes to +4. Okay, so that one can't work either. So we found it right there. So did you see how I worked that problem? Right. You saw what are the possible answers, right? Throw them up there, do the numbers, and then put them in order. Okay, 24, I'm gonna have to here. There we go. 24. Which of the following reactions is a non-redox reaction? Okay. So I'll just use this to tally. Calcium carbonate yields calcium oxide and CO2. Oh, we're gonna have to do that one. I was hoping we'd have a rule of thumb that would work on it, but CO2. Okay. Calcium, let's see, this is -2, -6. This is +2. So carbon is +4. How about this one? -2, -4, +4. Nothing happened to carbon. Calcium didn't change. And oxygen still. Okay, so that's not a redox reaction. Which of the following reactions is non-redox? Okay, that's a non-redox, A. This one, B, is redox. Right? So that one doesn't work. How do I know? Oxygen. In a compound here, element there. It has to be a redox. SO3, H2O, H2, SO4. Let's see about this one. SO3 plus H2O yields H2SO4. Okay, so that's +1, that means +2 total. This is a -2, means -8. So -6, this is a +6. Okay, -2 +1, we know that one, just memorize it. -2, -6, +6. Non-redox. So A and C are both non-redox. More than one correct answer. Okay. And let me go ahead. Scroll that one. Can I get all 3 of them on there? Yep. 25. Which of the following statements concerning oxidation reduction is correct? Okay. They cannot occur independently of each other. Yeah, that's true. If you have an oxidation, you've got to have a reduction. They never occur separate. They accompany all chemical reactions. That's false. They describe respectively gain and loss. Oxidation is loss, not gain. So that's reversed. And not more than one. Okay. So we found our answer. It's A. And this redox reaction, iron plus oxygen plus hydrogen chloride yields iron 3 chloride plus water. This reaction, reducing agent, oxidized. Okay, so we need to assess the oxidation states of each one. Let's see if I can do that on the board. This one's 0, 0. This is -1 plus 1. This is +3 minus 1. And there's a -2 plus 1. Okay. So iron is being oxidized. Right, it goes from 0 to +3. Loses electrons. So if we go from here to here, that's a loss. Oxygen is being reduced. That's a gain. Okay, hydrogen doesn't change, chlorine doesn't change. Okay, we got our major players. Now we can look for the answers. HCl is the reducing agent. Is HCl? No. Nothing happens to HCl. Okay? It can't be a reducing agent or oxidizing agent because it didn't change at all. Oxygen is the substance oxidized. Nope, it's reduced. Okay. Iron undergoes an oxidation number decrease of 3 units per atom. Now it's an increase from 0 to +3. More than one correct answer? No correct answer. Right. I forgot to write 26 up there. My apologies to the viewing audience. 27. In a redox reaction, the oxidizing agent is the substance. We've covered that. It's the substance that's reduced, the oxidizing agent. So it's the substance that contains an element that undergoes decrease in oxidation number. Yep. When you decrease the oxidation number, you have to add electrons because that makes it go more negative. That's what they mean. So you can go from +6 to +4, and that's a decrease. Or you can go from 0 to -4. That's a decrease. You have to think of it in those terms. So C is the answer. All right. Let's see. Okay. 28. For a collision between molecules to result in a reaction, the molecules must possess a certain minimum energy. Did we do this before? Oh, and they recover the minimum energy, but that's not all that's required. In order for the reaction to occur, they have to have a certain amount of energy. Plus, they have to be oriented correctly. Right? If the reaction site is on this side of the molecules and they come together like that, nothing's going to happen. So they must have a favorable orientation. That's also required. Let's see here. 31. Chemical equilibrium is reached in a system when? Let's see, complete conversion of reactants to products has occurred? No. Doesn't have to happen that way. Reactant and product concentrations are equal? No, not necessarily. Reactants are being consumed at the same rate as they're being produced. Yeah. That talks about reaction rates. The forward reaction rate equals the reverse reaction rate. Then you have equilibrium. And that can occur, it's dependent upon the reaction itself, whether you have mostly products or mostly reactants. And that will be reflected in the K. A large K means mostly products. A small K means mostly reactants. All right. Okay, I've got both of them. According to Le Chatelier's principle, which of the following effects will occur if ammonia is removed from an equilibrium mixture? If you remove ammonia, which way is the reaction going? That way. So the concentration of nitrogen will increase? Nope, it'll decrease. Heat will be generated. Yeah. Right. If you remove this, it's going to drive the reaction to the right, which makes more heat. It's exothermic. So B is a good answer. Concentration of H2 will decrease. Yes. Remove that. It's going to consume some of that to make more. So actually, two of the answers are correct. More than one is correct. Okay. How about 35? I forgot to write the number again. 35. For which of the following equilibrium systems will the equilibrium position shift to the left when a stress of increased pressure or a decrease in volume is applied? Okay, so for pressure to make a difference, you have to have gases involved. Plus, you have to have a different number of moles of gas on one side than the other. So let's see, how many moles do we have on this side? We got 9 moles of gas on that side and 6 moles of gas on this side. So if we increase the pressure, it's going to move to the right because you want to, the response to an increase in pressure is decrease the number of moles of gas. That relieves some of the pressure. So no, this one will shift to the right when we do that, not to the left. 2 moles here, 2 moles there, no change. Pressure change won't affect this reaction at all. How about this one? 2 on this side, 2 on that side. No, won't affect that one either. Okay, so E, no correct response in that question. All right. Oh, lovely. One of these. We already know this part. We just need to look at these and see which ones are true. Let's see. 39. And number 1, is it true? The only information needed to write an equilibrium constant expression is a balanced chemical equation with physical state information for the reaction. To write the expression, yes. Right? We don't have any numbers, right? We're just writing the expression. Okay, so 1 is true. How about 2? The oxidation number of sulfur is the same in the species H2SO4 and SO4 2-. Here's the trick to that one. This is the polyatomic ion, and this is the polyatomic ion. Sulfur will have the same oxidation number for both of them. So 2 is true. About 3, increasing the concentration of a reactant makes collisions between the reactant and other reactants less likely because of more crowded conditions? I don't think so. Makes it more likely. Okay, so 2 of the above would be B. 2 of the 3. All righty. Oops. Let's go down here and scroll up. So, oops, went too far. Sometimes I wonder if walking over to the computer would be quicker. There. Did we do this one already? No, we did. Did I skip any? 39. No, that's right. Okay. 45. Okay, so we got to check these out. 2, 3. Of the known atmospheric greenhouse gases, CO2 is both the most abundant and also the most efficient at preventing heat loss from the earth. False. Not the most abundant. What's the most abundant gas in the atmosphere? Greenhouse gas. Water vapor. Water vapor. It's not the most efficient at preventing heat loss, but it is the most abundant. How about 2? Ozone is a form of oxygen in which there are 3 atoms per molecule. That is true. That's ozone. A decrease in body temperature slows down the rate of chemical reactions. Yeah. So 2 of these are true. B. Don't ask me what one has to do with the other. I don't think they have. There's no relationship. 46. Okay, assign the following reaction to one of the reaction classifications given in the response list. Okay, let's see what we got here. We've got 2 complex making 1. 2 goes into 1. Is that a combination? I think so. It's like A plus B equals C is a combination reaction. It's not a decomposition. It's not a displacement. Not an exchange either. Okay, so it has to be a combination. Let's see. 49. Assign the following reaction to one of the reaction classifications. Oh, okay. So what do we got here? Potassium cyanide and hydrogen chloride yield hydrogen cyanide and potassium chloride. It looks like we've got an exchange reaction. Right? Sometimes we call it a double replacement, where the hydrogen and the potassium just swap places. So if we swap places here, that means HCN and KCl. Yeah. So that's an exchange reaction in your textbook. But you will see it called double replacement. And a displacement is often called a single replacement, where you have, say, A plus BC yields B plus AC, single replacement. And ready. Let's see. If I can do this. Yeah. 52. For the indicated element, select the correct oxidation number from the response list. I think we've done this before. H2SO4. Right, we can do it this way or we can do it this way. We already proved that. So this would be -8 hold us as -6 plus 6 plus 6D. I go too fast, or you caught that? Okay. 53. What's the oxidation number of carbon in KHCO3? We'll do this one whole. So that's a +1, that's a +1, that's a -2, makes a -6. When we combine those two pluses, we get a -4, so this has to be a +4. See. In fact, carbon dioxide, carbonates, they're all +4 carbons. That's as far as you can go with carbon. You can go from a -4 to a +4 in carbon. And living systems take advantage of that. They move those electrons in cells. And as the electrons move from the -4 carbon on their way to a +4, each step they take, they extract some energy from it. (56) Consider the redox reaction. Okay. Choose an appropriate chemical formula for the list that identifies the oxidizing agent. Okay, we need to find out which one's reduced. Okay, so we have -2 there, so it's +4 here. This one will be +6. All right, so it can't be, this one's not the oxidizing agent because it's oxidized, not reduced. So this one has to be the oxidizing agent. We could go through the rest of the rigmarole. What we found out which one's oxidized, that one must be reduced. So it's logical, and you want to get that answer quick, move on to the next question, right? If you're in the middle of a test, get her done. Let's see. Scroll that one just a hair. Yeah. Okay, 62. For the following general reaction, choose the correct form of the equilibrium constant expression from the response list. Okay, so we've got a solid here, so that one's not going to be part. We're only going to have this one on top. Concentration of Z squared divided by X, concentration of X squared. Here it is, B. (64) Consider the following equilibrium. Are we still in chapter 9?
Yes.
My goodness. Okay, I think there are quite a few in 10 also. I better pick up the pace. Consider the following equilibrium. Carbon dioxide plus hydrogen yields methane plus water. What's the effect on the position of the equilibrium when some CO2 is removed? If you remove CO2, which way is it going to shift? That way. So it shifts to the left. All right. 66. Looks like the same reaction. What's the effect on the equilibrium when a catalyst is added? Does not shift. Doesn't change the equilibrium position. It gets there quicker. It doesn't change the equilibrium. Okay, for the same reaction, determine the effect on the position when the volume of the container is increased. We decrease the pressure. So let's see, we've got a gas, 2 moles here, and we've got 3, both those are gases, 4 moles there. So if we decrease the pressure, which way is it going to shift? Increase the volume? Yeah, it's going to make more moles of gas. Right, it'll shift to the left. Yeah, let's see. Oh, now we're into chapter 10. Try to squeeze them all in there. Yep. Okay. All right, we start renumbering again. Okay, so this is chapter 10, 3. In this reaction, the Bronsted-Lowry base is, so by definition, an acid is a proton. A base is a proton acceptor, according to Bronsted-Lowry. So who's donating the proton in this thing? That one donates a proton. That's the base, NH3 minus. All right. 4. Which of the following is not a conjugate acid-base pair? Remember what we have to have for a conjugate acid-base pair. You've got to have this part of the molecule has got to be the same on both sides. And the base has to have lost 1 proton only. So let's see which ones match. That one, acid, that works. Oh, not a conjugate acid-base pair. I have to read my own writing, right? So this one is. How about this one? Yeah, it lost a proton and that bumped the charge up to 2 minus instead of 1 minus. Why? Because the proton comes off as a plus charge. It leaves the electron behind. So that's true. How about this one? H3PO4, H2PO4 minus. Yep, lost 1 proton and bumped the charge up to a minus. CO2 and CO3. No, there are no hydrogens there at all. So D is the wrong one. It's not a conjugate acid-base pair. Oh, I knew I was going to do that. 5. In which of the following pairs of acids are both members of the pair strong acids? So you have to remember what your strong acids are. Sulfuric acid is strong. Phosphoric is not. Hydroiodic is strong. HNO3, they're both strong. Yeah, so we found our answer really. That's a weak one, that's a strong one, that's a strong one, that's a weak one. Which one is this one? Recognize that? We're going to use that today in the lab. That's acetic acid. Sometimes we write it. Can I show you this one? Acetic acid can be written this way. Right. There's your acidic proton. Right. These protons do not dissociate, just that one. Or sometimes you'll see it written this way. That gives you a little more information about the structure, because it would be like this. That's this part. And then that's connected there, and then you have that one, that one, that one. And there's your acidic proton. This is called a carboxylic acid. Very common in biochemical reactions. Okay, so we got that one done. 6. In which of the following pairs of acids are both members of the pair polyprotic? So you need two or more protons that can dissociate. That means you look at the front of the molecule and see, do you have two or more? Right? This one's only got one. That ain't it. That's only got one. That's only got one. There's three. There's two. That's it. D. Okay, I'm gonna have to scroll this one. Yep. 7. Which of the following is produced in the first step of the dissociation of the acid H3PO4? So when we say H3PO4, then we're going to use the abbreviated version. Right? We're not going to transfer it to a water and make a hydronium. We're just going to say, all right, it's going to lose the proton. We know it's not independent, but the calculations work out the same. What's left over? Two of those. Still that one, and a minus. All right, so let's see what we got here. Two of those, there it is right there. That's the first step. You can do it 2 more times. You can lose another one, you can lose the third one. And each one of those will have a separate equilibrium constant. All right. Note. A solution of pH 13.3 is pH 13.3. Acidic or basic? Basic, yeah. So if you look on a continuum and you have a pH of 7, down to 0 here and maybe 14 there, these are all acid, these are all base. And this is neutral. Okay, but pH 13 is strongly basic, which should be there, right there. Okay. Uh, 12. Which of the following does not describe an acidic solution? Does not describe an acidic solution. Okay, so A, pH less than 7. That's acidic. The OH minus is greater than 10 to the minus 7. OH minus concentration is greater than 10 to the minus 7. That's basic. Right? So greater than this would be what? 10 to the minus 6, 10 to the minus 5, 10 to the minus 4. Right? Backwards. Oh, we found our answer then. If the hydronium is greater than the hydroxyl, it's acidic. If the OH is 10 to the minus 10, that's smaller than minus 7. So that's acidic, not basic. Okay, we found our answer. How about 13? If the pH of a solution increases from 3.1 pH, 3.1 to 5.1, the hydronium ion concentration increases or decreases. If you go from pH 3 to 5, it's less acidic. So it's going to be a decrease in hydronium. Right? So that means we can count out A and B are gone. Don't even have to look at them. C and D decreases by a factor of what? 1.6? I don't think so. pH is a logarithmic scale, which means if you move 1 unit pH, you move arithmetically, you move a factor of 10. Well, because this is log base 10, right? If it was log base E, you move by a factor of 2.3, something. But in this case, it's by a factor of 10. So we moved 3.1 to 4.1 to 5.1. That's 10 squared 100 times. Okay. Routine 14. In which of the following pairs of salts will both members of the pair hydrolyze in water to give solutions that are basic? Okay. The way this question is worded, we don't have to go to the chemical. We don't have to investigate it chemically. What we can do is use the rule of thumb. Look at the sources of the cation and the anion. If we're looking for a basic solution, that means we want a cation, this part of the molecule, that's derived from a strong base. And the other part of the molecule derived from a weak acid. Strong base, weak acid. So we look at each one. Both pairs will give basic. Okay. So lithium hydroxide and hydrochloric acid, those are both strong. That should be neutral. So that one doesn't work. We can skip that one. This one is ammonium hydroxide, is a weak base and a strong acid. That should be acidic. Okay. So that one doesn't work. Sodium acetate. Sodium hydroxide is a strong base. Acetic acid is a weak acid. So our rule of thumb says this one's going to be basic. Sodium hydroxide and HF. HF, F may be a halogen, but HF is a weak acid. Hydrochloric acid, hydrobromic acid, hydroiodic acid, those are all strong acids. But the top member of that group, the halogens, HF, makes a weak acid. It's the exception to the family, the black sheep, if you will. So that means C will satisfy. Basic, basic. Okay. And that's simply based on our rule of thumb. Now, we didn't dig into the chemistry here to say, why is it basic, right? It's basic not because of this actually, but because of that and because of that. Because when you put those in solution, then they react with water. And if this is derived from a weak acid, it's going to go for protons wherever it can find them, right? Because it didn't want to give up protons in the first place. So if you got water in there and it takes protons from water, what do you got left? Hydroxyls. So that's where the basic nature comes from. Not from this part, but from that part. But to answer our question, our rule of thumb works fine. In a solution buffered at a pH of 9.5, okay, the addition of a small amount of acid will cause the solution to have a pH approximately 9.5. If you're only adding a small amount of acid, it'll be pretty close to 9.5. Besides, the acid would not make it jump a whole unit. So none of these others would be valuable. Definitely not that one. But this one's too far and that one's way too far. So 9.5 is the best answer. Now, if you have a pH meter that will read out to 3 decimal points, you'll probably see a shift, but it won't be much. Okay, 20. Determine the concentration of an acid used in an acid-base titration. Determining the concentration of an acid used in an acid-base titration always involves completely reacting a measured volume of acid with a known volume of, it has to be a base. So a base of known concentration. If the acid is an unknown concentration, one of the partners of that reaction has to be known. Right? We're going to do that today. We're going to first thing we're going to do is find out the true concentration of our base, sodium hydroxide, by titrating it against a known concentration of acetic acid. Then once we've established the concentration for the base, we're going to use that to titrate against citric acid. And then use the stoichiometry that we know for citric acid to calculate the molar mass of citric acid and compare it to the accepted value. Oh, so A is the answer. All right, 24. In which of the following pairs of acids are both members strong acids? Did we get this one before? I think this is repetitive. Both are strong acids. All right. And maybe some, I think it's the same question, but different choices. That's a strong acid, but that's not. Right? Nitrous acid is a weak acid. That's a strong acid. That's a weak acid. Strong acid. There you go. See, hydrochloric acid and perchloric acid. In fact, perchloric acid is stronger than hydrochloric acid. Okay. Let's see. Do I need to scroll down? Some of them are A through D and some of them are A through E. There we go. 29. In which of the following indicates an acidic solution? Okay. 7.5. Greater than 7 is basic. So that's false. Hydronium ion concentration 10 to the minus 5. Greater than 7, 10 to the minus 7. Yeah, that's acidic solution right there. How about this one? Hydroxyls equal to 10 to the minus 8. So this one's true. Hydroxyl ion concentration is equal to 2 times 10 to the minus 8. Okay. What does that mean? Well, it has to be greater than 10 to the minus 7, right, in order to be basic. But that's less than 10 to the minus 7, isn't it? Yep. So that means this one's also acidic. So more than one correct response. Let's see here. Oh, joy. Both members of the Bronsted-Lowry conjugate acid-base pair must contain the element hydrogen. No, not necessarily. If it's a monoprotic and it loses the hydrogen, it won't have one anymore. Right? So that's false. How about 2? The larger the value of the acid ionization constant for an acid, the weaker the acid. If the Ka is increasing, that means the numerator is getting bigger. That means you've got hydroniums and conjugate base increasing. So you're actually increasing, you're making a stronger acid. So that was false also. How about 3? Weak acids cannot completely neutralize strong bases. No, they can neutralize strong bases. They do it at a different pH. Right? The pH at equivalence is different. for each one, actually. But no, weak acids can, right? So none of the statements are true. They're all false. Another one, formation of a coordinate covalent bond is always part of a Bronsted-Lowry acid-base reaction. A coordinate covalent bond. No. I don't think that's true. What is a coordinate covalent bond? That's where two parties contribute an electron each. No, where one of them contributes both electrons. So is that true? Formation of a coordinate covalent bond. Bronsted-Lowry acid-base reaction. That may be true. So if you say, if you have an acid and water's like this, okay, then if that proton leaves, it's going to bond here. Yeah, that's true. Yeah, number one is true. Because both of those electrons came from water. Right? That's the only example we need to satisfy the conditions of that statement. So one is true. I'd think about that one for a minute. The compound H2CO3 is both a strong acid and a diprotic acid. No, I don't think so. Carbonic acid is very weak. Right. If it were a strong acid, you'd have a whole lot of trouble drinking pop. Because that's the acid. That's one of the acids in pop. The other acid they typically put in there is phosphoric acid, but it's a weak acid too. And they put it in there so that the carbon dioxide will be more soluble. You can get more carbon dioxide in it. So when you open the cap, it goes. Do you ever notice when you put your pop bottle, before you open it, stick it in the refrigerator, get it cold. That makes the gas more soluble in the liquid. So when you open it up, there's not as much fizz. Then you can pour it over your ice and it'll do a whole lot more fizz. Because, well, that's another topic. How about two? Okay. It's a diprotic acid, but it's not strong, right? So that's false. The pH of the solution with OH minus. Okay, so if this one is equal to 1 times 10 to the minus 8, then is the pH equal to 6? How would you approach that? Preferably the easy way. Calculate POH. Right? What's the POH? POH is equal to 8, right? And remember, 14 is equal to pH plus POH. So if this one is 8, that one has to be 6. This one's true. So two of them are true. 2 of the 3 statements are true. There you go, right there. Okay. That looks that's a bonus type right there. That twisted my brain up, so I can imagine what it would do to yours. 40. Okay. In aqueous solution, Arrhenius acids undergo ionization and Arrhenius bases undergo dissociation. I think it's the other way around. No, that's right. Yeah, acids ionize to produce the hydrogen ion. And bases are a combination of a cation and a polyatomic anion. And all they have to do is dissociate. But acids have a covalent bond between those two, so they must ionize. Okay, so one is true. Two, production of salt, NaNO3, through a neutralization reaction involves the reaction of a weak acid with a strong base. All right, so remember, when you react an acid with a base, you always get salt and water. So we look at the origin. Where did sodium come from? Strong base. Where did the NO3 come from? Strong acid. So 2 is false. Okay. Three. The ion product constant for water at 24 degrees has the numerical value 1 × 10⁻14. Yeah, the ion product. That's the KW, which is this one times this one. And for water, it's always going to be, well, for pure water, is our starting point would be 10⁻7 here, 10⁻7 there, which makes it 10⁻14. So that was true. So 2 of them are true. All right. My goodness. I shouldn't complain because I did this to myself. 1. The 2 members of Bronsted-Lowry conjugate acid-base pair will always differ from each other by 1 unit of charge. Yes, because when you lose a proton, it leaves electrons behind. And that means a negative charge between the acid and the base, 1 negative charge. So that's true. An equivalent of an ion is the molar amount of that ion needed to supply 1 mole of positive or negative charge. That's a definition. That's an equivalent. Yeah. In an acid-base titration, the indicator changes color when the reaction between it and the added acid is complete. Let me read that again. In an acid-base titration, the indicator changes color, that's true, when the reaction between it and the added acid is complete. I guess that's one way of saying it. I think there's a better way to say it. The point is that the indicator, like that, that's usually the way we write it. The indicator is doing this kind of thing. Oops. There you go. It's in equilibrium also. So if you're adding hydrogen ions, then you're taking it back to this side. And at some point, the difference in this color and that color favors that color, and you see the change. Okay, so if you've got an indicator in your acid-base reaction, like we're going to use today, phenolphthalein, then at a certain point, yeah, it's raining. We're on the top floor only. Okay. Then the point is that there's a reaction going on between the added hydrogen ions and the indicator too. So ideally though, the consumption of the hydrogen ions by the indicator will not affect the titrating reaction itself, because you only put a little bit in there, and you go for a very vivid color change with just a little bit of stuff. So it's a trade-off. And so, okay, so 3 is true. All 3 are true. And I'm gonna have to. My goodness, are we supposed to be getting all this rain? Okay. Yeah. Well, I don't have to leave till, if it stops raining, I'll be okay. Right. You don't want that creek to flood. 45. Give them time, okay. 1, all rainfall, even in unpolluted areas, is acidic. True. Right. All it has to do is dissolve some carbon dioxide, makes carbonic acid. So rainfall is always acidic. Blood plasma, interstitial fluid, and intracellular fluid, all contain electrolytes. Yeah. You got sodium, potassium, chloride ions, those are all electrolytes. Blood plasma is slightly acidic because its ion contains undergo hydrolysis. Nope. It doesn't matter this part. That's false. Blood plasma is very slightly basic. Let's see. Remember what that is? I think it's buffered between 735 and 745. It's a very narrow range. So if you're diabetic and your system goes out of whack, it's going to go acidic, and it's going to make you very, very ill very quickly. That's because your body's trying to use, is creating acids and ketones, basically. And that leads to acidification. But carboxylic acid, that group I showed you before, COOH, makes those, and ketones. Okay. 49. Hope we're getting close because I don't want to run over. Select from the response list the compound or ion that best fits the description. Reacts with H3O plus to form HPO4 2 minus. Okay, what's going to react with hydronium? It's going to have to be a base. It's going to be a proton acceptor, right? Because you can't cram any more protons on that molecule. It can't be a base. It has to be an acid. So if you're going to transfer a proton from this one to something else to form this one, still on there, just barely. So what's going to be in here? What's going to accept a proton to make it that? There. Because you add a plus, take that down 2 notches, and there's your hydrogen from there. So we're looking for this GO4 3 minus, right there. So you have to sort of think backwards on that. Like a lobster or a crawfish. I like crawfish better. They have a better taste than lobster. And they're more up. You ever been to a crawfish boil? Ah. With the whole works, right? Boiled potatoes, onions, yeah, corn. And they just dump it out on the table, go to town. And when you get full, you just keep cracking. Take some home with you. Let's see here. Oh, can I squeeze it in? Yeah. 54. Select from this list, response list of the acid that best fits the description. An acid that has more non-acidic hydrogens than acidic hydrogens. And here you have to know the difference between the two. The acidic hydrogens are always the one in front. They're going to be these guys right here. And the non-acidics are these. So we need more non-acidics than acidics. Right? So we have, that one doesn't have any non-acidics. We got 3 more, 3 to 1, 2 to 2 is equal, and those are none. Okay, so B has to be the answer. Acetic acid. Get 5. Select from the response list for the acid that best fits the description. An acid that completely dissociates in solution to produce negative ions with a charge of 1. Completely dissociates. Okay. Negative ion with a charge of 1. Okay, this one will do it. Hydrochloric acid is a strong acid. This one will dissociate completely for the first hydrogen. You know, that's a bad question. A and D both work, right? Because sulfuric acid, when it dissociates, makes that plus this with a charge of 1 minus. Okay, so I need to make a note. That's a bad question. I don't even have 55. Should be. Oh, no, I'm not. Your brain's working better than mine. So this one could be A or D. All right. So if one like that shows up on the test, you can call me on it. Hopefully I'll have it figured out before then. 56. Best fits description. A salt whose dissociation produces equal amounts of 2 ions. A salt. So we look for the salt. That's not a salt. That's not a salt. That's a salt. That's a salt. Which one produces equal amounts? Well, K3PO4, which is kind of off screen there. K3PO4, how many ions does it produce? Well, it produces 1 anion, but 3 cations. So that's not equal. But this one produces 1 of these and 1 of those. That's equal. So that's what B is the answer. And goodness. There. Just the last one. Okay. Good. Good. We'll finish in time. What's the pH of a buffer that is 0.250 molar in a weak acid? There's your acid. And 0.26 molar in the acid's conjugate base. The pKa is equal to 5.53. Okay, how are we going to solve this one? Now you need an equation. Anderson-Hasselbalch. So you look in your useful information at the back. Did I include that in this document? You don't have that copy. Yeah. In the composite, oh no, I didn't. Okay. It's fair. If I forget to put it on the exam, ask me for it, I'll give it to you. Inners and Hasselbalch. We can calculate the pH of a buffer if we know the pKa and the ratio of the conjugate base to the acid. Okay, so all we have to do is plug in the numbers here. Let's see, this one will go on top, 0.260. This one on the bottom, 50. Take the log of that. And then we want to add 5.53, and that'll be our pH. And in the interest of time, it should come out at 555. And that's typical for buffers. The best buffer pH is going to be the one that's closest to the pKa. Because if these values are equal to one another, the conjugate base to the acid, what does that give you? Log of 1. And what's the log of 1? 0. 10 to the 0 power 1. So once you decided about, well, if you decide that you've got a weak acid that's going to be the base of your buffer, then you know where you want that buffer pH to be. If you decide that you need a buffer pH of a certain value, then you look for the weak acid that's got a pKa near that value. Okay. Phosphoric acid. How many buffers can you make out of that? You can make 3 different buffers because it's got 3 protons and they're all weak. So a lot of biochemical buffers that are used in cell cultures and other types of things are based upon phosphoric acid. They call them phosphate buffers. And they just adjust them in which range. Because when you titrate phosphoric acid, there's pH. And here's added base. Base. You're going to get something like this. Here. See, 1, 2, 3, there. So you're going to get 1 there, 1 there, 1 there for each of the protons. Okay, we are finished.